Greetings and welcome. Oops, I see a little mistake. It is 2017. Welcome to week 6 in geometry. We are in the week of February 14th, 2017, not 16. Happy Valentine's Day if you are viewing this on Tuesday. I do want you to make sure you've got your math notebook out and you're ready to take good notes. That's going to help you with completing the assignments this week. So, I do have a warm-up that we're going to practice some probability that we learned last week. And here we go. So we've got 10 marbles that are in a bag. In that bag, there are 2 red marbles, 3 green marbles, 3 orange marbles, and 2 purple marbles. And I want you to tell me what is the probability of choosing a green marble. And then I want you to tell me, is this question an example of experimental or theoretical probability? So go ahead and click pause and take a moment to complete this in your math notebook. All right. So hopefully you click pause and you've worked through this on your own, because you will get more out of these types of practice problems if you're actually clicking pause and working through the problems on your own first before you see the worked out solution. So if we were going to find the probability of green, one way that we might see this written is a capital P with parentheses and green in the parentheses. That is one way of writing the probability of choosing green. And you're going to see probability written like this throughout this unit. So I wanted you guys to get familiar and comfortable with seeing notation like that. So we would use that notation, and then what is the total number of marbles we're dealing with? So what are the total possible number of marbles that we can choose from? So we've got 10. It says we have a total of 10. So that's going to be my denominator, because that's the total number of marbles that I can choose from. We want to find the probability of choosing a green marble. So we see that there's 10 green marbles. So we have 3 different green marbles to choose from to create that probability of choosing a green marble. So the probability would be 3 out of 10. Remember, we can also write probability as a decimal. So to get that into decimal form, I would just take 3 divided by 10 and I get 0.3. And we can also write probability as a percentage. So to move that decimal to a percent, I'm going to take the decimal and move it 2 places to the right. So 2 places to the right, and that would be 30%. So if there's a 3 out of 10 chance, that's a 0.3 chance, which is also a 30% chance of choosing a green marble. So was that question an example of experimental, or theoretical probability? So this is an example of theoretical probability, because we are writing our probability based on what we expect to happen. Experimental would be as if we actually took tallies, if we reached into the bag of marbles and took tallies about which color we picked each time, and then based the probability off of those tallied numbers. So because we didn't do that, because we're just basing it on the information that's given to us and what is expected to happen, that is an example of theoretical probability, which we learned last week. All right, so moving right into this week, and this week we're going to look at session 2 and session 3 in Schoology in Unit 6. So Unit 6, session 2, and session 3. And let's start with session 2. So session 2, you guys are going to explore dependent versus independent probability. So you're going to see those words and those vocab words this week. So let's look at them and understand what they mean in more depth. So dependent. So when we're talking about dependent probability, we are looking at one event that affects the probability of another event. So an example of that would be like picking a card from a deck of cards and not putting that card back, and then finding the probability of something else. Another example would be if you have, again, a bag full of marbles, and I asked you what the probability of choosing a green marble is. We found it. Well, let's say that now we keep that green marble in our hand and we do not put it back into the bag. And I ask you now what the probability of finding an orange marble is. Well, that probability is going to be affected by the first action that I took of holding on to that marble, because now there would only be 9 marbles total. So dependent is when you've got one event that's affecting the probability of another event. Whereas independent events, just like independent, means one event has no impact or influence on another event. So our events have no bearing or impact on another event. An example of that would be rolling a dice and picking a card from a deck of cards. So rolling that dice is in no way, shape, or form going to affect which card is picked from a deck of cards. If we were to go back to the marble, our bag of marbles, if I were to pick a marble and then put it back into the bag, it's not going to affect or influence my next choice when I reach in and pick out another marble, because we'd still be choosing from that total of 10 marbles. So that's the difference between independent and dependent events when we talk about probability. So dependent and independent events. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. So when we're talking about independent probability or independent events, remember that's when one action does not influence another outcome. So the result of the second event is not affected by the result of the first event. Let's talk about how we find independent property, or how do we go about finding independent probability. So we are going, let me take a step back. If we have events A and event B, so let's call our first event A and our second event B, and if those events are independent events, then to find the probability of both events occurring, so to do that, what we're going to do is we're going to find the product of the probabilities of each independent event, or each individual event. And remember, product means when we multiply two things together. So here is the notation that I mentioned before that we're going to see a lot, and it's important that we understand the notation so that we understand the formulas that we're given. So if we have two events and we call them A and B, and they're independent events, then to find the probability of event A and event B occurring, that's what that means, capital B with the parentheses, A and B. That means the probability of finding event A and B happening, that's going to be equal to, if we find the probability of the first event and multiply it times the probability of the second event. That is how we find the probability of independent events. So let's take an example. It always makes a lot more sense when we look at an actual example. So we've got a drawer where we've got a bunch of paper clips. And in that drawer, we've got 3 red paper clips, 4 green paper clips, and 5 blue paper clips. So 1 paper clip is taken from the drawer and then put back into the drawer. So it's an independent event because we're not holding on to that paper clip. We're putting it back. We're not changing the total number of paper clips. So that means it's an independent event because we're going to choose another paper clip from the drawer after we choose our first one, put it back. We're going to choose another one. So we want to find the probability that the first paper clip is red and that the second paper clip is blue. So that's what we're trying to find, the probability that the first paper clip is red and then the second one is blue. So we're going to find that independent probability. So the first thing we want to do is we want to find the probability of reaching in and grabbing a red paper clip. And then we're going to multiply it times the probability of reaching in and choosing a blue paper clip. So let's find the probabilities. How many total paper clips are there? 3 plus 4 plus 5. So 3 plus 4 is 7. 7 plus 5 is 12. So we've got a total of 12 paper clips. How many red ones are there? There are 3. So we've got a 3 out of 12. And then we're going to multiply that times blue. How many blue? There's 5. So 5 out of 12. And then we're going to do the math. So we're just multiplying those two probabilities. Multiplying fractions, I go straight across the top. I get 15. 3 times 5 is 15. 12 times 12 is 144. So then if I wanted to write that as a decimal, I could. I could say 15 divided by 144 is I'm going to go to 2 decimal places, 0.10, which as a percentage is 10. So the chances of us reaching in first, grabbing a red paper clip, and then reaching in again and grabbing a blue paper clip, we would have a 10% chance of that happening. So overall summary, when we've got independent events, where the second event is not affected by the result of the first event, we've got an independent event, and to find that probability, we're just going to multiply the two events, the probability of each together. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. Otherwise, here we go. And now, let's see here. Let's look at dependent events. Let's look at dependent events. So remember, dependent events is when the result of one event is affected by the result of another event. How are we going to find the probability of dependent events? It's going to be a little bit different what we just did with independent events. So let's focus our attention here to this box. So if we've got event A and B, and they are dependent events, so the results of B are affected by event A. So if we've got these A and B events and A occurs first, then the probability of finding the probability of event A and B occurring, we use this formula. So first, we're going to find the probability of event A, the first event. Then we're going to multiply it times the probability of the second event once the first event has occurred. So looking down here, this is where we get our fancy notation. So the probability of event A and B occurring is going to be equal to the probability of event A times the probability of event B once A has occurred. So that's what that B and then this line A means, is event B once A has occurred. So again, let's look at an example and it's going to make a lot more sense. So we've got our same drawer full of paper clips. Again, we've got a total of 3 plus 4 plus 5, so we've got 12 total paper clips. So we're going to reach in and grab one paper clip, and then we're going to hold on to that paper clip. And when we're not going to put that paper clip back. So for our second reach in, we're only going to have a total of 11 paper clips to choose from, because we didn't replace the first one. We're going to hold on to it. So what we want to do is find the probability that when we reach in for the first time that we get a red paper clip, and then when we reach in for the second time that we get a blue paper clip. So again, remember, when we don't put that paper clip back, we're changing the total amount of paper clips we have to choose from. So let's find the probability. So we're going to find the probability of getting a red and blue, but we're not replacing. So this is a dependent event. So we're going to find the probability of the red, and then we're going to multiply it times the probability of choosing the blue once the red has already been chosen and not put back. So the probability of choosing a red, we've got 3 red, so it's 3 out of 12. And then the second chance of choosing a blue, there's 5 blue, but now there's only 11 total to choose from. So our denominator is going to be different there. So let's do the math. 5 times 3 is 15, and then 12 times 11, really it's our denominator that's changing in this case, is 132. Again, I can change that to a decimal. 15 divided by 132, I get 0.11, or an 11% chance of that happening. So we had a different probability than when we replaced the paperclip. So holding on to that paperclip is going to affect the outcome of our second reach-in and choice. I'm going to go on to the next slide, so if you need more time, go ahead and click pause now. All right, so just a quick summary. So remember, probability is the number of ways something can happen divided by the total number of outcomes. Dependent events, such as removing marbles from a bag and holding on to them, are going, so dependent events are affected by previous events, where independent events are not affected by previous events. And let's move on to session 3 and two-way tables. So session 3, you're going to be focusing on two-way tables. So a two-way frequency table is going to deal with 2 variables. Remember, 2 variables is another way of saying bivariate data. More than we've got 2 variables, bivariate. And the tables are going to examine, in two-way tables, we're going to examine the relationship between two or more categories. So here's an example of a two-way table. So we've got a survey question, and we're asking a group of people, if you could have a new vehicle, would you want a sports utility vehicle, an SUV, or a sports car? And we created a two-way table to represent the responses we got. So in our survey, we're asking a group of people that were composed of males and females. So here I've got the rows telling us of the males, we've got 5 that wanted an SUV, 7 that wanted a sports car. And then out of the females, 9 wanted an SUV, 4 wanted a sports car. So you can see the two-way table, we're comparing 2 sets of bivariate data, males and females versus SUVs and sports cars. So what's cool about two-way tables is we can pull all sorts of information from this table. So in addition to just collecting the data of whether you wanted a sports car or an SUV, we can also find the total number of people asked. So I'm going to put total here because we're going to find the total for the columns and for the rows. So how many total people wanted an SUV? So the number of people who wanted an SUV is this column right here. So we're just going to add 5 plus 9 and get a total of 14. So 14 people wanted an SUV. More specifically, of those, 5 were males and 9 were females. Sports cars, how many total people wanted a sports car? Well, that was 7 plus 4, which means that there's a total of 11 people who wanted a sports car. More specifically, 7 males, 4 females. Now we can talk about the total number of males that were surveyed. The total number of males was 5 plus 7, which is 12. Total number of females is 9 plus 4, which is 13. Then we can add those columns and those rows together. So if there was a total of 12 males, 13 females, how many total people were surveyed? 12 plus 13 is 25. You can also see if we added our totals over here of all the different sports cars, there would also be a total of 25. So what you're going to see this week as we work through two-way tables is that we can have the totals of our columns and our rows to give us even more information about our two-way tables. So we can add our columns, we can add our row totals, and then we can add all of our totals to find the total number of people that were surveyed. So 25 would be the total number of people surveyed. And what's cool is that you see that the columns, 12 plus 13 is 25, as well as our row totals will also equal 25, 14 plus 11. I'm going to go on to the next slide, so if you need more time with this slide, go ahead and click pause. One thing I forgot, I just wanted to say that, so these total columns, so our total columns here, all of our totals, when we talked about the columns and the rows, these columns, totals, are marginal frequencies. So we call this our marginal frequencies. Oops, running out of room. Frequencies. Marginal frequencies. And then all this stuff, all the information in the middle of our table, so all this right here in the middle of our table, that's called our joint frequencies. This is called our joint frequencies. Okay, so now I'm really moving on. All right, let's go ahead. I'm going to fill out the totals again really quick. All right, so what we want to do now is find, we talked about how all the information in the middle is the joint frequencies, but now if you look, I have a new word up here, joint relative frequencies. So joint relative frequencies, relative, is the values in each category divided by the total number of values. So remember, 25 is our total number of values. So if we want to find the joint relative frequencies, we're going to take the value in each category and divide it by the total number of values. And that's going to give us our joint relative frequencies. So example here. We've got 5 males who wanted an SUV, so to find the joint relative frequency, we would take 5 and divide it by 25. So 5 divided by the total number of people surveyed is 25. So when we do that, 5 divided by 25, I plug that into my calculator and we get 0.2. So 0.2 is my joint relative frequency for that column and row. For the females, I'm going to do the same thing. I'm going to take 9 divided by 25, and I'm going to get that into a decimal form, which is 0.36. So I'm going to keep going. 7 divided by 25, plug that in my calculator, I get 0.28. And 4 divided by 25, divide that, and I get 0.16. So all these numbers here, these are all my joint relative frequencies. So the decimals are my joint relative frequencies. And then I can do the same thing for my marginal relative frequencies. So remember, the marginal values were those total values. So the marginal frequencies are the totals. So I'm going to do the same thing. I'm going to change my colors up since we're talking about marginals. I'm going to take 14 and divide it by 25, and I'm going to get my decimal, 0.56. And then 11 divided by 25, I get 0.44. I'm just plugging these in my calculator. 11 divided by 25 is 0.44. I'm going to do 12 divided by 25. Plug that into my calculator. I get 0.48. And then 13 divided by 25, and I get 0.52. So now, just like remember before, I added my totals 12 plus 13 to get 25. 14 plus 11 gave me 25. What about if I add my marginal frequencies? What do you think I'm going to get as my total? if I add my marginal frequency. So if I take 50.56 and add it to 0.44, what do I get? And then I should get the same number when I take 0.48 and add it to 0.52. What do I get? I get 1. I get 1. So that's always going to be a rule when you add your marginal frequencies, when you add those together, you should always get a total of 1. You should always get a total of 1. That will always happen when you add your relative marginal frequencies together. So the relative word is when we have our decimals. If we're just talking about joint frequencies and marginal frequencies, we're talking about the numbers that we started with. But once we start using the decimal format, dividing each of those by the total number, we're going to get our relative frequencies. So pretty cool. Lots of things that we can find from two-way tables. Let's answer some questions about two-way tables because you're going to be doing that in this week's assignments, and I want to make sure you understand how do we do that. So lots of different information here. Remember that the original numbers are still within. Here's our original numbers. I'm just going to circle them in yellow so that we can see those. So the first question says, what percent of the survey takers were males? What percent of the survey takers were males? Well, how many total survey takers did we have again? How many total survey takers? Remember, there's 25. And out of those 25, how many were male? So we want to focus on the ones that were male. All these were male. This whole column right here, those were our males. So 7 plus 5, we had a total of 12 males. So 12 is going to be our numerator. So we would have 12 out of 25. If we want that as a percent, we've got to go from a decimal to, or from a fraction to a decimal, which is 0.48. Move our decimal 2 places to the right, and we get 48%. So 48% of the total people who took the survey were males. All right, moving on to the next question. I'm going to get rid of that highlight so it's not confusing. It says, if a person is a male, what is the probability that they will choose an SUV? So how many total males did we have? We just talked about that. We had 12. We had a total of 12. And out of those 12, how many chose a sports car? 7 did. So we'd have a 7 out of 12 chance. 7 out of 12, that's 0.58, which is 58% if we want to take it to a percentage. All right, one more question and then we'll stop here. If a person chooses a sports car, so now we're talking about sports cars, we're talking about that column. If a person chooses a sports car, what is the probability that they are a female? So if they choose a sports car, what is the probability that they are a female? So how many people chose a sports car? 7 plus 4 is 11. And then out of those, how many were female? 4. So 4 out of 11 is 0.36 or 36%. So you're going to be looking at two-way tables this week and answering lots of different questions about two-way tables. So again, just to kind of see what we did so far, we looked at how we can have a two-way table with just joint frequencies and marginal frequencies. So just taking the total numbers, and then we can actually find the marginal relative frequencies and the joint relative frequencies where we're taking each value in each category and dividing it by the total number to get those decimal values. And if we add all of our totals together, we should have a total of 1 when we add those marginal relative frequencies together. And that's all. Let me put up. Alrighty, so for your week of February 14 key phrase assignment, here is our situation. You are going to roll a dice and you're going to choose a marble from a bag. So very general question here. I want you to tell me whether that situation involves independent or dependent probability. And then tell me why you chose independent or dependent. So if you're going to roll a dice and choose a marble from a bag, would that be an event? What type of probability are we talking about here? Independent